What's up, everyone? Here are the solutions for the week 10 quiz. And for the first problem, we're asked to compute a limit. And notice as x goes to 0, both the top and the bottom of the fraction go to 0, which means we get to use L'Hopital's rule, right? So this limit is equal, by the 0 over 0 case of L'Hopital's. We can replace this by the limit as x goes to 0 of, take the derivative of the numerator, so that's going to be cosine of x minus 1 divided by the derivative of the denominator, which is 3x squared. And again, if we try to plug in 0 for x, on top I get 1 minus 1, which is 0, and on the bottom I get 0 again, so I have to do L'Hopital's one more time. So this is now the limit as x goes to 0 of, the derivative of the top is going to be just negative sine of x divided by 6x, right? I bring down the 2, multiply by the 3, I get 6x. And now, because x goes to 0, this quantity right here, this is a special limit, we know it's going to go to 1, so the whole thing goes to negative 1 over 6. If you didn't remember this fact, the fact that the limit as x goes to 0 of sine of x over x goes to 1, you could also just redo one more iteration of L'Hopital's, and you end up with negative cosine x over 6, which is going to go to negative 1/6, because at this point you can plug in, you no longer get 0 over 0. So either method is fine, and that's the solution for the first problem, negative 1/6. Now for the second problem, we are asked to sketch a graph of some function that satisfies the following conditions, right? So right away I'm going to start just by drawing my axes here, and what I'm going to do is I'm going to just, at a quick glance, x equals 2, I see a 4 in here, I see a 1, so I'm going to label this up until, let's say this is 1, this is 2, this is 4, and maybe one more tick mark on there, right? I also have some y values here, f of 0 is 0, I have f of 2 is negative 1, and I will just make the y-axis scaled a little bit differently, just to make things a little bit easier to see. So let's see what we have here, right? Before I draw it on the final graph, I'm going to label all these things. So 0, 1, 2, 4. And let's take a look at what happens, right? I have f prime of 2, 0, and f of 2 is negative 1, so that's going to be either a min or a max, right? We have a horizontal tangent because of the derivative of 0. My function is decreasing between 0 and 2, so it should be going like that, which kind of gives me a hint that's a min. And it's increasing for values larger than 2, so it looks like that, right? So the general shape should look like that. Also, if we look at the second derivative, I get some concavity information. I get that the function is concave down between 0 and 1, and a decreasing concave down function is going to look like that, but it's going to be concave up between 1 and 4. So now I'm decreasing between 1 and 2, concave down, I hit my minimum, then I go all the way at, I still remain concave up here, that's a inflection point. I still remain concave up until 4, and then I become concave down again, right? And all throughout this interval from 2 to 4, in fact from 2 to infinity I'm increasing, and from 0 to 2 I'm decreasing. So let's take this and let's put it on the final graph. So yeah, I get f of 0 is 0, that's 1 point, f of 2 is negative 1. Let's connect these 2 points using this piece here. So I have concave down, inflection point, concave up with a local min. Then I am going to be concave up until 4. I don't necessarily have to hit 4, but then I become concave down again. And notice I have a horizontal asymptote at 1, so let me fix this a little bit. Maybe I'll go up to here. Then I'll start to level off towards that asymptote, just like so. Okay, so that's what the graph should look like. But notice I have an extra condition which gives me some symmetry in the graph, right? And this is basically saying that I get to reflect this over the y-axis. So everything that I have here, I'm just gonna copy it down, and that's essentially the final graph.